me some time. So here you all are able to, okay, so you are able to see that this particular, we will be giving a complete self-explanatory guide from perceptron to regularization, which comes as the unit one of the deep learning subject. So let's see, go to the next slide and we'll see what is this deep learning. I know this is a little revision, but today we will be looking into the link of one topic with another topic and how they are related, and then what are the disadvantage of one technique and why how the disadvantage is overcome by the another technique. So here, so before diving into the definitions and formulas, let us know the shape of the journey. So today this deck is not just a list of unrelated topics to memorize. Over here, it is a single unfolding story. It begins with the simplest possible artificial brain cell and watches its fail, and then follows step by step the reasoning, and then the why every other model has come in the market. Now let's see what is this deep learning. So deep learning is a subset of machine learning that uses the neural networks with many stacked layers. So as there are many stacked layers, they are called as a deep. So it automatically learns the patterns and features directly from the raw data and instead of human handcrafted features. So over here, we can see that there is a difference which is listed. So we have the feature extraction. So in this traditional method, it's a manual. In a deep learning, it is automatic. The data requirement of deep learning is a huge. Hardware is also required, a GPU, TPU. Even the interpretability is a little harder in the case of the deep learning, and the complex data analysis is done in an excellent manner in the deep learning. Now let's see why it has emerged. So as the data volume grew massively, the data can be the images, text, speech, or the sensor data. The GPUs made the large scale computation practical and affordable. So traditional machine learning, it hits a ceiling on the complex unstructured data. And so it has given the rise of the deep learning network, which begins outperforming the engineers who were working the traditional machine learning pipeline. So, as we say that the deep learning is the best understood as a branch of a machine learning in which the learning system is built out of many stacked layers of the small computational units. And the word deep simply refers to how many of these layers are stacked on top of one another. So what it makes this approach special is that the system is not told which features of the data matter. It discovers these features entirely on its own. So purely by looking at the example. So this automatic feature learning ability comes at the price, right? So though the understanding that price explains why deep learning did not become the popular the moment it was invented. So the additional machine learning could get away with modest amount of a data and an ordinary computer processor. So it's a decisions where they're relatively easy for the human to interpret and explain. So over here, the deep learning is sometimes like a black box. For a new person, it is difficult to understand the layers of the deep learning. Now let's see, like we always say that the single layer perceptron is there, and there is a disadvantage of single layer perceptron, and there is a XOR problem. So let's look into why and what about this, and why the single layer is not enough, or why one single layer of the neurons is not good. So the most basic building block of a neural network is the single neuron, which is called as a perceptron. This perceptron makes its decision using just a straight line. You can see it on the graph. It's like a flat plane. So if we are just differentiating between red and blues, it is easy to do the red and blue dots. It is easy to separate out with the single straight line. Then it fits in this single layer perceptron. Fine. But again, please remember there is a but. But if these blue and red dots are mixed in a curvy or this circular pattern, then this straight line will not fit. Over here in the graph also, you are able to see a straight dotted line. But think of that these red and blue dots are mixed with the curvy and circular patterns. Then it is not easy to differentiate them with the straight line, or it is not easy to separate them with the straight line. And this is our classic XOR problem. I hope you have understood what is this classic XOR problem. So imagine a harder puzzle version. The red and blue dots are tangled together in a curved, almost a circular patterns, weaving in and out of each other. So no matter how you rotate or how shift a single straight line, some red dots will always end up on the blue dots, and some blue dots will always end up on the red side. So this is not a limitation of effort or the training time. It's mathematically impossible. So this is our famous problem, which is called as a XOR problem. I hope you all have understood the XOR problem. And so now we will move and see like how this XOR problem is solved. So who is going to fix this XOR problem? So this XOR problem is fixed with the multi-layer perceptron. See, the question has beautifully a simple answer. It's called a multi-layer perceptron or MLP. So rather than relying on a single neuron making one straight line decision, an MLP arranges neurons into the layers. An input layer that receives the raw data, one or more hidden layers which are sandwiched in between, and there is an output layer which produces the final answer. So I hope you have understood the solution for this XOR problem. The solution to XOR problem is my multi-layer perceptron, which is my MLP. And what does it to do? It has the input layer, it has one or more hidden layers, and the lastly, it has the output layer. So with every neuron in one layer connected to every neuron in the next. The reasoning behind why this fixes the earlier problem is, of course, the worth walking through to it. Let's go and see what is the reason and how it is fixed. So because it is one of the most important intuitions in in this complete subject. So if a single layer can only draw one straight line, then a second layer receives the output of the first layer as its own input, can combine the several of those straight lines together into something more elaborative. So layer by layer, these simple linear pieces get stitched together into increasingly complex curved shapes. Returning to our earlier analogy. So it's exactly like joining several straight fences, panels, end to end until collectively they form a closed circular fence that correctly encloses every flower. And so this is how this MLP solves the XOR problem, which is given by the single perceptron. And here it is a foundation of the depth, the stacking of many layers. This is what is our foundation of the modern neural networks. You must have noticed that everything said so far describes only the architecture of the network, right? Its shapes, its wiring. It says nothing about information actually travels through that wiring to produce an answer. Correct. And so this the next mechanism which we'll be looking into will give the answer of how it is going to modify the data and give the answer as the data travels through this wirings or these layers. Correct. So moving ahead, we'll see the feed forward neural network and which is going to answer to our question. So feed forward simply means the direction of the data flow in an MLP. So input, hidden layers, and output with no loops, never going backward. So each layer's output become the next layer's inputs, like the water flow one way through the pipes. So it is used to make the prediction, inferences. So why feed forward? So the information moves strictly forward, a one-way street, never backward. So there is no real limitation here. This is just the mechanism for producing an answer. But still, now you can sense something is missing, right? So over here, again, I will explain what happens exactly. So data enters at the input layer, passes through each hidden layer in turn, and finally arrives at the output layer. So always moving forward, never looping back on itself. A helpful mental picture is water flowing through a system of one-way pipes. So each layer receives whatever the previous layer sends it, transforms that input in some way and passes its own output onward to the next stage with no way for the water to flow backward through the pipe. So this is how the Single line data flow is over there, or single directional data flow is there. So this feed forward is path is exactly what happens every time a train network is asked to make a prediction or a brand new data. So this act of making a prediction is technically called as the inference. So, but here there is again a catch, as it's an important one. So everything described in this slide assumes the network already knows the correct values for all its internal weights. So it says absolutely nothing about how these weights got get set correctly in the first place, right? So what we are assuming, it has assumed that everyone knows the weights, right? But then how does this weight comes in a picture? So that's the missing part. The actual learning process is the subject of next two slides. So this is going to turn out like require moving the information in the opposite direction. See, again, I will repeat. So what we have seen here, we are looking at the forward feed forward neural network. So over here, we are claiming that the data is moving in single direction or in a one direction only. Now, looking at like here, we have assumed that they know the exact internal weights. But as we know that the weights has to be calculated at each turn. It has to be calculated, recalculated, re-verified. But how does it comes? So it comes through the back propagation. So now looking at like what is back propagation and why it is needed. Correct? Now let's see. So the deep network can have the thousands, millions of weights, right? So when a network makes a wrong prediction, we can't manually figure out which knob to turn, right? So on by how much there are too many, and each one contributed a different amount to the mistake. So what does this backpropagation do? It works backward from the final error, layer by layer, calculating exactly how much weight contributed to the mistake. So using the chain rule of calculus, instead of blind guessing, every weight gets a precise calculated update instruction. So let's take a simple analogy. So let me explain this back propagation with the analogy. So if your team lost a match, any cricket match, football match, right? So you must have seen this football World Cup match also. So let's consider that your team has lost a match. So back propagation is like reviewing the game in a backward direction. How will you review that? So you will review by asking the question that we lost because of the last over, or that happened because of the dropped catch in the 30th over. Or going backward, we can say that which happened because of the poor fielding practices. So like this, we are going back and finding out the reason of the loss. Correct. So similarly, in the neural network, for every pass, whenever there is a wrong prediction, we will be going back in a layer by layer manner, and we will be finding out the reasons for the error. Correct. But still something is missing. So the back propagation calculates the direction and the size of each weight's error contribution. And but knowing it doesn't fix the weight by itself, right? It back. What does the back propagation do? It goes back. It calculates the direction. It size of each weight's error contribution, but it cannot calculate the weight. Doesn't fix the weight by itself. So again, I will explain. So back propagation is the elegant solution, right? Rather than guessing. Correct. But instead of what happens is, as I give you the analogy of the cricket match or the lost in the football match. So this backward chain, what is do? Instead of the coach reasoning about the season, it calculates the reasoning about the layer of neural network, right? The single person saying no, it will be calculating the reason of the error by layer by layer. So it's worth pausing on one or more crucial details before moving on. So back propagation only tells us the direction and the size of each weight's mistake. It does not by itself change the single weight. Please remember, it just tells us the direction and the size of each weight's mistake. Does not correct the weight. So something else has to take the calculated instruction and actually act on it. And when I say that something else who is going to calculate the weight and who is going to act on it is the gradient descent. I hope you have understood now what does this gradient descent is. Again, We'll check like what does actually happens, how the error flows back. So the error is a signal and is computed at the output and when propagated backward through every layer by layer back to the input. So there are few steps. So the steps are the network makes a prediction and compares it to the correct answer. This gap is the error. So starting at the output layer, backpropagation calculates how much each weight in that layer contributed to the error. It then moves one layer back and repeats using the chain rule. By the time it reaches the input layer, every single weight has a precise correction instruction waiting for it. I hope you have understood this. So again, I will say, what does it do? So this process continues layer after layer, moving steadily from output towards the input until finally every single weight in the entire network, including those buried deeper near the input layer, has received its own precise correction instruction. So only once this entire backward journey is complete does the network have everything it needs to actually begin updating itself, which brings the story for our gradient descent. I hope you have understood this. Again, I will say, see, what does it do? The network makes a prediction. Now that prediction is compared with the correct answer, right? So there is a gap. Now this gap is my error. The gap between the predicted answer and the correct answer is my error. So this error is propagated back with the back propagation. And at every layer or at every neuron, it know like what is the reason and why it is like how much is to be corrected, right? So that happens at every layer, like wherever the error has happened. And now the weight which are going to be changed are to be done with the gradient descent. Now we'll see the gradient descent. Okay, let's look at the gradient descent concept. Now what is this gradient descent? The gradient descent is the optimization method that actually updates the weights using the gradients computed by the back propagation, moving step by step toward the lowest error. I hope you have understood this. What does the gradient descent is? The gradient descent is the optimization method, right? So gradient descent is optimization method that actually updates the weights using the gradients computed by backpropagation, moving step by step toward the lowest of error. Right. We'll see the simple analogy. Okay, so the simple analogy is say you are standing on the hillside and completely enveloped in the thick fog, trying to reach to the lowest point in the valley. Correct. Again, I will repeat. So you are standing at the hillside and there is a fog, a thick fog all around you, and you wanted to reach to the valley point, which is the lowest point. A spot that represents the point of the lowest possible error, correct? So you cannot see the overall shape of the landscape from where you are standing because there is a thick fog, but you can feel right under your own feet which direction slopes downward. So you take a small, careful step in that direction, pause, fill around again for the next downward slope, and take another step. So repeating this process patiently again and again until you finally arrive at the bottom. I hope you understood. So what is the example of this gradient descent? A simple analogy. The analogy is you are standing at the hill and you wanted to reach to the valley and there is a thick fog. So what you will do, you are not able to see anything. So what you will do, you will start taking the small steps. You will start taking the small steps and you will be going down by taking careful steps and sensing around, right? And then you reach to the bottom. So each one of these small steps corresponds to exactly one update of the network's weight. And this tipping process is repeated thousands upon thousands of times during a full training run. Of course, but there is a genuine danger hidden in this process, and it depends entirely on how large each step is. Correct. Take steps that are too large, you risk striding right past the valley for floor and bouncing chaotically from one hillside to the another, never settling down, right? So a state called instability or the divergence. And if you take steps that are too small, you will eventually reach the bottom technically, but the journey could take impractically long time, right? So there are of course advantages and disadvantages of taking these steps, a small or the bigger steps, right? So getting the step size right, right? So what is our aim over here is to get this step size right. It turns out is one of the most delicate balancing acts in all of the neural network training. I hope you are clear with this. So what we have to do in the gradient descent, we know that we have to take these steps, small steps to come to the destination, to for the convergence. But then we have to decide upon the step sides, and that is the a very balancing act, correct? And that again we'll see how to decide this step sizes. So moving ahead about again the gradient descent and the different types of this gradient descents. Like so what we have to do, the checking the entire data set before taking even one downhill step is extremely slow with millions of data points, which is all called as this batch gradient descent. Right? Now there are multiple types. We'll see everyone one by one. So the second important design decision buried inside the gradient descent that we haven't yet addressed is how much data should be examined before taking each downhill step. So this single question splits the gradient descent into three distinct flavors, the which we have listed over here. So these flavors are like, let us see like what are the importance of these flavors and how they exist. So the most straightforward approach is my batch gradient descent. So it looks at the entire training data set before computing even a single step. So this produces a very accurate, stable sense of which direction is truly downhill, since it's based on the complete information. Are you getting this? This batch gradient descent is on the information, a complete. It is on the basis of complete information. But once your data set grows to the millions of example, right? If you have a huge data set which has the millions of examples, recalculating this over the whole data set before every single step is really a painful and impractically slow task. I hope you have understood this. So the disadvantage of this batch gradient descent, though it is going to look at the entire information at a time, but when you have a huge number of data points in your data set, it is really painful to recalculate it for every step, to recalculate over whole data set before taking a single step. It is really a painful task. I hope this is clear. So then in direct reaction to this slowness, we have the stochastic gradient descent, which is my SDG. This SDG swings to the opposite extreme. It looks at just one single example before updating, making it extremely fast, light on memory. Again, I will repeat, what does this stochastic gradient descent do? It swings to the exact opposite direction. It looks at the one single example, only one single example before updating and making it extremely fast and light on memory. But a single example is noisy, unreliable, and snapshot of the whole data set. So resulting the downhill path becomes jittery and erratic occasionally. Even sometimes you may land in stepping in the wrong direction entirely. And so we have one more solution. This one more solution is a mini batch gradient descent. It emerged as the natural compromise between these two extremes, the examining a small handful of examples, commonly 32 or the 64, before each update. So this gives a reasonably reliable sense of direction while still remaining fast enough to be practical, which is exactly why mini batch gradient descent is the version used almost universally in a real world training today, right? So you must have noticed that the recurring pattern over here. So because it repeats again and again throughout this unit, the batch was accurate but slow. So SDG was invented to be fast, but the SDG turned out to be noisy. So mini batch was invented to balance the both competing demands with the same rhythm. Right. Now look at like what happens next. Correct. We have come the gradient descent. We have seen the single layer neuron. We have seen the multi-layer perceptron. And then we have seen like why do we require this gradient descents? And then what no, no, first we have seen the feed forward, then the back propagation, and then what is this gradient descent? And now the types of this gradient descent. But there is something which is called as the vanishing there is something which is called as the vanishing gradient, right? So what is this vanishing gradient and why it happens? So when the back propagation sends the error signal backward through many layers, it gets multiplied by a small number at every layer. So multiplying many small numbers together again and again makes the result shrink towards the zero. Again, I will repeat. So when the back propagation sends the error signal backward through many layers, it gets multiplied by a small number at every layer. Correct. Error signal jar hai piche and then it is getting multiplied with the small number. So multiplying many small numbers together again and again makes the result shrink towards the zero. I hope you have understood this. So the effect of this is by the time the error signal reaches the earliest layer, it's basically zero. So those layers stop learning, even though the rest of network trains fine. A simple analogy I will tell you. A whispered message passed backward through the 50 people gets a little quieter each time. And by the last person, it's a silent. Correct? And this is what is called as the vanishing gradient. So in the real world consequences of this mathematical fact is very serious. By the time error signal has traveled backward through many layers and finally reaches the earliest layer, the one sitting closest to the input, it has often shrunk to something indistinguishable from zero. So those early layers receive essentially no meaningful correction signal at all. And as a result, they barely learn anything. So even while later layers closer to the output continue training just fine, the clearest way to feel this phenomena is to imagine the whispered message, as I said. Fine. So now we'll see like again, like what is this vanishing gradient and which functions are risky for this vanishing gradient, correct? So naturally the next question is why does this shrinking happens with such a severity and as it is avoidable? So answer lies specifically in which activation function a network happens to be using. So because of a different functions produces very different size derivatives, the two activation functions that dominated the early years of the neural network are sigmoid and tanh. You must have heard of this. So the solution for this vanishing gradients is through the activation function. And these famous activation functions are sigmoid and tanh. Right. So both squash whatever input they receive into the narrow output range. And critically, their derivatives are always small numbers. So sigmoid's derivative, for instance, never rises above 0.025, no matter what the input it receives. Multiply several numbers that are each at most 0.25 together across say 10 layers, and the result becomes vanishingly tiny almost immediately. So this is the precise mathematical mechanism behind the telephone game faded we just described. Then there is a ReLU. So ReLU by contrast has a derivative that is always either exactly zero or exactly one. And repeated multiplication of ones never shrink at all. So this single mathematical difference is why the field needed and eventually found a genuinely different family of activation functions and why this search has become required for us. So we'll see few activation functions. So Let's see these activation functions one by one. So we have the trend of activation functions, correct? So we have seen the trend over here, and then we have seen this functions ReLU and Licky ReLU and eReLU. So now let's see like how does this activation function works and what does this do? Say, correct? So having just diagnosed vanishing gradients as fundamentally an activation function problem. So it makes sense to zoom out and precise the entire solution before examining each phase individually. So activation function doesn't exist to decide whether and how strongly a given neuron fires in response to its input. Without them, no matter how many layers are stacked. So the entire network will mathematically collapse into behaving exactly like one single boring linear layer. Correct. So the history of activation functions that follows is we have multiple activation functions. So we have the functions like the ReLU, ReLU, correct, and Licky ReLU, l- like this. So we'll be looking into this all functions in the next session.